In this session, let us have a look onto the application of metal organic frameworks in biomedical field or pharmaceutical field. Metal organic frameworks are potential candidates for biomedical applications since there are many biocompatible metal organic frameworks based on biomolecules. And applications of MOFs in biomedicine are quite immature, but this field of research is progressively growing. In mid-2000s, MOFs were used for controlled drug delivery and as a contrasting agent in MRI, magnetic resonance imaging. MOFs are emerging areas of interest for researchers, serving as a contrasting agent in MRI scanning, both in T1 and T2, that is spin lattice relaxation time-based and spin-spin relaxation time-based MRIs, or it can also be used in combined form of T1 and T2 scanning, MRI scanning. They are also used as a targeted drug delivery or for combinatorial application in both MRI and diagnosis. MOFs can be modified functionally and structurally by conjugating with other biomolecules as a bioligand. Then biopolymers can also be added for specific delivery of drugs. MOFs can be designed as pellets or tablets, thin films or patches, then composite materials based on polymers or inorganic materials. For example, silica covered MOFs or patches can be developed, or stable solutions of nanoparticles with modified surfaces. So, if we can develop patches based on metal organic framework, we can absorb, for example, insulin on those patches and we can stick that on our body. Then there will be controlled release of insulin to diabetic patients. MOFs can be used for biomedical applications due to their versatile properties like high adsorptive nature, not absorptive, high adsorptive nature, porous structure, precise drug release and storage capability. A wide range of drugs with hydrophilic, hydrophobic and amphiphilic properties can be easily accommodated in MOFs. We know there are different varieties of MOFs. Some can have hydrophilic properties, some can have hydrophobic properties, or there are MOFs where we can introduce functional groups showing both hydrophilic and hydrophobic nature. Okay, so drugs of different nature can be stored or adsorbed within such MOFs and they can be released. So MOFs are good candidates for drug storage and delivery. Drugs can bind covalently or non-covalently within the MOF depending on the nature of the drugs and the target site. In MOFs, drugs can be tethered through biomolecules or encapsulated in the core of MOFs. Okay, they can be connected or attached to the biomolecules or ligands present in MOFs, or drugs can be captured within the cavity of metal organic frameworks. For drug delivery, many factors have to be considered, such as pore size, conformation of MOFs, and pre- and post-synthetic modification possibilities. All these can affect the physico-chemical properties of MOFs and their drug delivery efficiency. These factors corroborate the capacity of MOFs to carry the drug, absorption properties, stability, and release at the target. So, MOFs has to be carefully tuned for drug storage and delivery. Some important factors that has to be considered during the development or application of MOFs for biomedical applications are the biocompatibility of the material, biotoxicity, then tissue responses, cell viability, cellular uptakes, then size, shape, structural and morphological properties of the MOF. So, we can summarize that the material should be safe to be administered. It shouldn't bring any side effects. MOF-based drug delivery systems, DDS drug delivery systems, are formed by either by encapsulating the drug molecules in the nano cages of MOFs to achieve drug delivery and sustained release in tumor microenvironment. This is the principle you see here in this first picture. Here we have a metal organic framework and the drug molecule, what you see in red and white is the drug. It is encapsulated, it is adsorbed or trapped inside the cavity. This is the encapsulation strategy. Then there is another mode of drug storage, development of drug delivery systems, where the metal organic framework itself is built using the drug as the connector. Okay, here we have metal centers, biocompatible metal centers, and the drug itself is used as a ligand. So our system is made up of drug. When it reaches the target site, it collapses and the drug will be released there. Okay, so it is direct assembly strategy, and this is the modern one. These days all are focusing on this post-synthetic strategy, where we have a biocompatible metal organic framework, and the drug is attached to or drug is post-synthetically added to the surface of a metal organic framework. Okay, so these are cargo molecules or drug molecules. And when it reaches the target site, by changing the pH or conditions, this drug will be released there. Okay, so there are two classical strategies, encapsulation strategy, then direct assembly strategy, and now the post-synthetic strategy. There are several metal organic frameworks which are explored for biomedical application. Some of them among are iron-based Biomil-1. So here it is called Biomil because the ligand used there or metal used there biocompatible. Biomil-1 MOFs exhibited up to 75% drug carrying capacity. Then zirconium-based MOF UIO66 embedded with silver nanoclusters is also used for targeted anti-tumor drug delivery systems. Then hydrophobic nano drug delivery system was designed using RGD, where they are amino acids, modified camptothecin at zeolitic imidazolic framework as a unique MOF for enhanced and targeted cancer therapy. Try to remember some of these examples. Then another potential field of application of MOF is in the bioimaging. So there are MOF-based bioimaging techniques. Bioimaging like MRI relies on large doses of administered contrast agents to differentiate between normal and diseased tissue. So when they are doing MRI scanning, especially of the brain and all, they inject contrasting agents. So some of these contrasting agents should last longer, and they may not be good for our body. So normal contrasting agent, they have to be used in higher concentration to differentiate the affected tissue from normal tissue. But MOF-based contrast agents provide high contrast enhancement. So they can be used in very small amount, and they will provide the sufficient contrast enhancement. Okay, so very little concentration of MOF would be sufficient compared to the higher concentration of other conventional materials used. Then there are MOF-based biosensors to sense biologically important metal organic frameworks. So these MOF materials can be modified on electrode surface. I hope you remember the physical chemistry unit that you have studied, electroanalytical technique. So based on that, these materials can be used to develop chemically modified electrodes, and it can be used to sense different analytes. Similarly, if they have fluorescent property, fluorescent sensors can also be developed using metal organic frameworks. It is very useful in the biomedical field because tumor markers or other biomolecules can be effectively detected at very low concentration in real samples using MOF-based biosensors. So they have high sensitivity, good repeatability, and a very low detecting limit of the order of 10 raised to minus 12 molar concentration can even be detected using such MOF-based biosensors. So very low detecting limit in the sensing of substances due to high surface area of such materials. MOFs can be used for the detection of lung cancer diagnosis as well. So here also there are some examples. There is a luminescent PLNP at CIF8. So another MOF is grown on the surface of CIF8. So it has a durable luminescence near infrared, which facilitates tumor site activated luminescence imaging. So we can use this particular material as a contrasting agent. So it shows durable luminescence. The luminescence lasts for a long time. So it is easy to detect the affected area and later do any manipulations in that affected area because the luminescence lasts for long. So this particular MOF produces persistence near IR luminescence for hours, or even days, and thus enabled background interference-free long-term and keep tissue penetration and imaging without external irradiation. The porous framework CIFID shell provided a high anti-cancer drug loading capacity, and acidic tumor site activated drug release was effectively achieved. So this anti-cancer drug can be loaded in this particular CIFID framework, and when it reaches the tumor site, because of the acidity of the tumor site, the system becomes flexible and it releases the drug there in the affected tissues. Okay, so you can see the representation here. So on CIF8, the PLNPs are grown, so we have a caution-like structure. Then drug is loaded inside. So when pH is in basic range, minimum basic range 7.4, it remains as such, and when it is acidic, the drug is released on the affected tissue, and it shows persistent near IR emission. So you can easily detect the presence of affected tissues there. Okay, so we don't need to use laser. Then another application as like MOF based antibacterial nanomaterials, presence of metal nodes in MOFs, such as if the metal organic framework contains metal nodes like silver, copper, nickel, zinc, etc., and some functionalized ligands having certain functional groups, and the high surface areas and adjustable forces of MOFs together promote excellent antibacterial activity. We know many of the coordination complexes itself are having this antibacterial property, antimicrobial property. So MOFs having with their enhanced properties effective more efficiently as antimicrobial agents. Okay, so it can act in different ways. We know in the case of bacteria, these drugs destroy cell wall, right? So MOFs can directly get accumulated on the cell wall and destroy the cell wall, or the linker can be, only the linker can be released and gets attached to the surface, or only the metal ions gets released and gets attached to the surface, and that destroys the bacteria. So these are some of the applications of metal organic frameworks in biomedical field. Thank you.